Okay, hopefully with a little work I should be able to make it so you can actually make videos and download them from the website. Your website in progress. I already have an example with how Three.js does it here. And I think I got through enough for a fair number of the annoying hoops with configuration that you need to do. So write file, hopefully I can just write these PNG files. Then fetch file, I need a reference to this canvas, which I think I have. Should be this. Oh, let me change the name of this ref from canvas to canvas component. So it doesn't get confused with the actual canvas. So that should be canvas component, that should be canvas component. Then this is the actual canvas. And from that, I can say let canvas be this from the canvas component. Great, now that I have that. Now I think, if I'm lucky, this code should just run. I should be able to write these PNGs. Canvas is not defined. Did I define it here? Oh yeah, this should be component. Okay. Fetch file. Which this is from the FFmpeg API. I'm trying to open that. Okay, this looks like it's running. Kind of slow, for better, for worse, or at least it's going. Also, if it's already logging, if it's logging just from calling FFmpeg, there's no real reason to log again myself. But okay, so that seems to be working. Fortunately, there's a lot more you have to do to actually read this from a video. I'll just see what Three.js does next. So we write all of these files, which for me they should just be black. What does this progress variable do? ffmpeg.set progress. Let me see what that is. A progress handler. Interesting. So it passes a function to handle progress info? Progress.set value. This isn't a function though. Oh, this is a function, so it takes a ratio and then does that. So set progress, then set value, but it's just calling set value here. Okay, I don't think that's necessary. Yeah, set value isn't here. I guess I don't know what this progress object is. A UI progress. Okay, so that's some 3JS thing. This is just for showing some reflecting the amount of progress that's done. Great. So I'm gonna do that. I'll try just running this command verbatim. So go to this, that loop, then here. Get rid of all these extra spaces. Actually, this should probably be just split up on multiple lines. Oh wait, did I mess something up? Single quote there. Comma, enter. Okay, pattern type blob, this. Okay, hopefully that makes that a little easier to understand. It looks like I just gotta run that. Don't know what CRF is. And FPS isn't a variable. So I'll just make that 60. I don't know why this is 5. I'll have to see what CRF is and FFmpeg. Constant rate factor. Use this rate control mode if you want to keep the best quality and care less about file size. This is the recommended rate control mode for most uses. This method allows the encoder to attempt to achieve a certain output quality for the whole file when output file size is of less importance. Okay. Well, if it's good enough for 3JS, I'll just see if that doesn't crash. So it runs through all these frames pretty slowly, admittedly. Okay, didn't log anything positive or negative. Wait, I should log something at the end of this. Like that. To make sure that's actually finishing. Also, there's no reason to do this for 60 frames. Can we just do 10 or something for now? I can have the FPS still be 60. Wait, it's like running it twice or something. Abort out of memory. Well, that's unfortunate. P thread aborting. Darn. Worker.js.on message captured an uncaught exception runtime abort out of memory build with S assertions. Well, if that happens with only 10 frames, let me see if bringing down the frame rate helps this at all. Same thing. So this makes me think there might be something else, something up with this that's making that happen. Let me see if there's anything about this on the GitHub. Abort this one. It's a fairly small file. I mean, the example works fine. I'm able to use the command in grabbing screenshots too. The worker thread is not closed. As a result, the memory usage is getting higher and higher. And this person just closed it, of course. Manually terminating the worker can solve the problem after poking around all the glue code. Found a function named exit. Well, this is already running in 3JS. I wonder why it happened this way. I wonder if unlinking those files... Okay, I'll try doing the rest of this. I'll try doing the read file and then unlinking them, and maybe that'll help. Great. Okay, so this writes the file. Then I'm gonna try reading it from this out.mp4. Then unlinking these PNGs. Okay. Okay, and it still happens. Pthread sent an error, blah, 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 blah. Worker.js captured an uncaught exception. Okay, and from here, it looks like it never logged this wrote file, so it's not even getting that far. I wonder if it's worth using this over... there's another version of this by someone called Kagami. And this is what I used before. And this worked. I wonder if it's possible these frames are too large or something, but it shouldn't be. Actually, I'm gonna check the memory usage if I can do that. Okay, and hopefully that'll finish soon. So this is just loading. It's doing this, write file. Fetch files at 0. Oh, I guess you pass this in a bunch of files. This runs ffmpeg. So run ffmpeg, get this data from reading the output, and it puts it into a video element. That's fairly simple. Okay, let me see. I guess there's no visual indication of what happens here. But I am able to see how much memory this ends up consuming. It doesn't matter, that's a long task though. 2 data URL. Most of it is 2 data URL. And several workers. Oh no, this is the same worker. Generic JS to WASM wrapper. And how many of these are there? Yeah, just a bunch. 5, 6, 7, 8. Well, I don't think this is happening once per frame. I don't think. What's possible it is. In raster, GPU memory is probably nothing. So most of it is these tasks, these WebAssembly ones. I wonder why it's happening so many times. That doesn't seem right. Although honestly, if this is having problems this early, for just an example, it makes me wonder if I should just switch. Template repositories for you to quick adopt ffmpeg WASM. Well, look at this. Hey Aquabeam, what's up? I'm just trying to use ffmpeg in WebAssembly, the usual. Yeah, it looks like this might not even work in the example. The shared array buffer is not defined. Just a regular Friday, you know. Well, this library isn't working. Let me see what the rest of the code was, because I managed to get around the error that this is seeing. Hey, Daryl Golden, what's up? fmpeg load. It's fetching this file variable, which I'm not sure what that is. Interesting dev meeting. What do you mean by interesting? Just some chatting. Okay, so my follow alerts work now, so that's good. And Haas 00312? Thanks. Some PRs in the transition. Gotcha. Over what it's worth, I'm glad you were able to make some progress in figuring out what those performance errors were about. Yeah, it looks like the main thing now is inverting the camera's model matrix to get the view matrix. Which I admit is probably pretty slow. I think matrix inversion is in general kind of slow. Do you know if Manim needs the shader wrappers every frame? Pretty sure it does. My understanding is that shader wrappers are just, they just hold the information about the object that's necessary for rendering it with OpenGL. And that you'll need no matter what. Seems to access it a lot less. Yeah, I think it's needed every frame. It shouldn't be needed like more than one time every frame. So if it's doing that, that could be a problem. I'll try running this with no arguments. Like 70 times less. Doing some model matrix math was hurting the performance. It could be the case. Model, like inverting? I can see inverting being slow. Definitely. The other operations on the model matrix were probably pretty fast, since NumPy is really heavily optimized for matrix operations. As for 70 times less, that seems like probably something with caching or something like that. Although, was that before or after you were doing it with the wrong frame rate? It's the read file. That makes sense. I guess this worked, quote unquote, but I'm not writing a video now. Let me try making both of these 30. Same thing. What is with this out of memory? I guess there's no way to tell when this is optimized as the P thread aborting. It could be the case that this needs some sort of P thread compatibility that I don't have. That's the only time P threads came up related to this library, I think. Dev dependencies. There's nothing mentioning it here. Getting WebAssembly things to work is always so difficult. Let's see if I can find anything regarding pthreads here. f.asm is undefined. Crashes with pthread error. Out of memory issues while transcoding. This is what I get. I think pthread aborting at error, blah 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 blah. Yeah. I have so many tabs open, man. And I'm not sure the extent to which I need them all. Might end up going back to this one. It's almost as big after all. Chrome on Mac OS. This person changed it a little. Always out of memory for file size greater than 100 megabytes. An error with React. Happens in HTML. Same problem on 0.9.7. Okay. So nobody understands this error. That's what it looks like. And as long as that's true, I don't think I can rely on this library. So that's fun. I did so much work to get this to work, too. I'll just say some random thing. ETN line from Manim web will be good to go. What do you mean by good to go? There's a few things. Well, there's a few like major benchmarks I want to do. The first one is getting it so that it can make video, which is what I'm working on now. And then, following that, I want to probably rebase on the latest version of Manim Community because it's on I think it's still on 0.8. I don't like this song. I think it's still on 0.8, so I want to rebase that. And then after that, I'll probably use it just to make videos. At that point, I would call it quote-unquote good to go. But the performance issues, if it like doesn't run all right on your current hardware, might take longer to resolve. Even though there are a lot of opportunities for optimizing that, it's just kind of hard to tell since my computers are so good. Yeah. Yep, that's me. I guess I do have some pretty strong GPUs. The thing about integrated graphics, I don't know quite how well that can be addressed well. Because I don't know if integrated graphics are strong enough for like shader optimizations to matter that much. Like, it's possible that it is. You know, I'll try. I don't know if I want to deploy this since it's buggy. Yeah, whatever. I'll just push this to Firebase. And see if it works any better when there's an optimized build. I don't think there will be. Get to Manim GL speed, it'll be fast enough. Yeah. I mean, the web version... For the web version, Python will always be a little slower, but JavaScript will always be significantly faster. But then NumPy will be faster than JavaScript. So there's this... I'd be pretty much incentivized to move everything away from vanilla Python that I can. And that's probably not something that's shared with the desktop version. Oh, this is a shared array buffer problem. Okay, yeah. I'm not going to try to use this. That's unfortunate. There's too many too many things they haven't figured out. Moving away from vanilla Python, we are already relying on NumPy arrays to move more things away from vanilla Python, I guess. The hierarchy, and so I'll say in local land, this is the speed hierarchy. Basically, Python is slower than NumPy. And actually, even in local environments, typically I think JavaScript is faster than Python. So I think it's something like this. But in webland, this Python, this like web Python or whatever, this is slower than regular Python. So this is slower than normal Python. But JavaScript on the web is faster than Python locally. Because JavaScript, it turns out, is the fastest interpreted language in the world. So basically on the web, all of the regular Python code is slower than it would be if it were local. And so what I want to do is move as much of the logic into JavaScript and NumPy as I can. That's what I want to do. But in the local land, that's going to be less of a concern, probably. They will want to move probably more things to NumPy, but JavaScript won't be an option. Okay, anyway, this is doing what it was doing before now. I'll just take out this FFmpeg stuff. To talk about Python slowness. I don't think it was ever designed to be as widely used as it is. And so that's probably part of it. Why is this slow? Why can't we make it faster? So there's... Well, I don't want to watch this whole thing now. There's one answer to this that's really... that's not interesting. Okay, I'm gonna... Hold on. Let me see if I can do some fancy schmancy stuff and actually put this on the screen. Because I do want to watch it. Image browser. Display. And I should probably learn how to freaking do this at some point. Like add sources. I wasn't trying to put it there. But I think that's good enough. Okay, try full screening this. Wait, not full screening it. This is hard, guys. I'm doing my best. Okay, so this window that I want to leave here and then play it.
Hi everybody, welcome to Virtual PyCon. Really excited to be able to give this talk today. It's about why is Python slow. It's quite a controversial topic, but hopefully we're going to get stuck into some facts here and focus solely on, I guess, engineering and science rather than opinions. So
More of
we're going to be digging
an
into a bit
interesting
more
talk.
about like the Python compiler
Yeah, I just
and
part of
where
this is
potentially there could be performance
I want to learn how
improvements
to
in the
do
future.
this
Secondly, I just want to say
because I'm
thank you for
pretty
joining.
bad
I
at
hope
it.
everyone is safe at home, and thank you so much as well to the PyCon organisers for being able to pivot around this crazy situation that's been happening so far in 2020. So yeah, hopefully you enjoy this, and let's get into it. So if I say Python is slow, it has to be compared to something. And to be more specific, when I talk about Python, I'm referring to CPython. So that's the version of Python you download at python.org, the one that comes bundled with macOS, and the one that's on the Windows Store.
Dude, this is so
if we take a look at a
difficult.
CPU intensive benchmark, this is the famous N-body program, which models the orbits of Jupiter, Saturn, Uranus, and Neptune, a task that we do on a regular basis. So the C in CPython is named after the language that it's written in. CPython is a Python interpreter written and compiled in C.
Wait to like crop
But
this.
if you compare the execution time of the same algorithm in C, it's 7 seconds versus 14 minutes. It's not even on the same planet in terms of performance. So maybe, C and CPython aren't really a great comparison. This is really apples and oranges. C is a strongly typed compiled language, and Python is a dynamically typed interpreted language. But what about Node.js? Node.js sits on top of the Google V8 JavaScript engine. It's actually a better comparison because it's also dynamically typed and it's interpreted as well. So what does Node have that makes it so much faster than Python when it comes to calculating the orbits of planets? So before I go into that, let's just recap how CPython actually runs code. So Python code is portable. You can download Python source files and they'll run on Windows, Linux, macOS. When code is actually read, it's parsed into an abstract syntax tree. This is a representation of what makes Python Python. It's a tree that represents functions, statements, operations, everything you'd expect to see in a Python application. So after completing the task of parsing, the interpreter has an AST with the operations, functions, classes, and namespaces of the Python code. The job of the compiler, though, is to turn the AST into instructions that the CPU can actually understand. You can't give the CPU an AST to execute.
That ruins everything.
The CPU really only understands like small instructions, small operations. It's essentially just a really powerful calculator.
Is it audible
now? The compilation task actually is split into two parts. There's the compiler, which traverses the AST because it's a tree, and it creates something called a control flow graph, or a CFG. The control flow graph basically represents like the logical sequence for how the code will actually run, not what the code is. Then there's the assembler, which basically goes through the control flow graph and then turns that into sequential statements, which are known as bytecode. This bytecode is really the atomic level of a Python application. It doesn't really go any smaller than that. In an evaluation loop, each of the bytecode instructions is taken and executed using something called a stack frame based system. Stack frames are a data type used by many runtimes, not just Python, but stack frames allow functions to be called and variables to be returned between functions. So stack frames contain things like arguments, local variables, and other stateful information, as well as the code to be executed, and the environment in which they live in, and also the thread in which they're supposed to run on. So a stack frame exists for every function call, and they are stacked. That's why they're called that. They're stacked in sequence in the terms of which order they were called in. You'll see a frame stack actually anytime you have an unhandled exception and it prints a stack trace. That's why it's called a stack trace. It traces up through the stack and tells you what frames are being executed when the error occurred. So reading, parsing, and compiling Python code is time consuming. It's a lot of work. It puts pressure on the CPU. So that compiled code is actually cached anyway. And this is what lives inside your dunder PyCache folder. And each time you run the code again, if the code hadn't changed, then the cache version is read, and read using the Marshall module. any optimizations above the line, so in terms of like reading, parsing, stuff like that, wouldn't make any difference to the benchmark because it's not actually going to impact how fast the code actually executes, because the CPython compiler is what's called an ahead of time or AOT compiler. So it's all compiled up front. When CPython executes compiled code, it uses like a central frame evaluation loop. It's in a file called ceval.c if you want to go and have a look at it. Takes a while to get your head around, but this loop is basically just a big for loop that goes through all the bytecode instructions, and it's got inside it a massive switch statement, and it says if it's this bytecode, do that. If it's that bytecode, do this. And it takes values from the value stack, which are typically variables, or they could be other things. It goes through each operation inside the loop, and it evaluates it. But because so much of CPython is based on top of compiled C code, a lot of the bytecode operations are in fact just calling compiled C functions. So why is compiled C code so much faster than CPython, which is just running compiled C code? Well, I think the clue is kind of in that loop. So each cycle of that loop is not free. It actually it's actually machine operations that need to go through for each bytecode operation. And the shorter the task, the shorter the time it takes to actually run the bytecode operation, and the more loops there are, the more significant that overhead becomes when you look at the time. Or actually, when you look at the benchmark, that's pretty important. So when you compare the n-body benchmark with C against CPython, it's absolutely slower because this benchmark uses really tight loops. It uses lots of really small arithmetic operations. They're not complicated operations. This is like add this number to this number, but do it like millions of times. So the CPython interpreter is basically just going around in a loop again and again and again, and it spent a lot of time just going around in the loop to get to the next bytecode. So if CPython could know that it's going to execute a tight loop, surely it could plug in some shortcuts or something, like it's kind of like short wire the loop. To understand that, we really need to actually look at the compiler and how the compiler works. So there are two types of compilers. There's an ahead of time compiler like CPython, or there's a just-in-time compiler, or a JIT. JIT compilers are very different because they compile just in time. They don't parse the code just in time. They parse the code ahead of time, typically, and then they use some kind of intermediate representation between the parser and the compiler. So this is a lower level. This isn't an abstract syntax tree. This is a lower level than that. And that happens at the pre-compiler stage, basically. It's not as concrete as a compiled code object like Python, but it's a lot lower level than an abstract syntax tree. So one of the big benefits to a JIT compiler is that it's really good at solving the tight loop problem. PyPy is a good example. PyPy is an alternative Python interpreter. You can use it to execute your existing Python code. It's open source and it understands Python 3.6 syntax. Also, unlike CPython, PyPy is written in Python. So the CPython compiler is written in C, the PyPy compiler is written in Python. Actually, the whole of PyPy is written in Python. So if my leading statement were true and Python is slow, then a Python compiler and interpreter written in Python must be like ridiculously slow, right? Well, actually, no, it's not. For the n-body algorithm, PyPy is actually 650% faster than CPython. So I'll just take a pause for that to sink in. There's a few reasons for this, but they all relate to optimizations. The problem we were looking at was the tight loop problem. And because PyPy uses a JIT, it's able to basically assess the algorithm and the data flow and make decisions about how it should be executed. It can change the execution structure just in time rather than having that all determined up front. The execution structure is optimized to the problem set that it's been given. So JITs are really effective at repetition and loops. So if they can assess the problem set and say, this is a lot of repetition here, these are known as hotspots. And what JIT compilers can do is they can say that piece of code is going to run a lot, so I'm going to make that really efficient. And it does have an overhead, which we'll talk about. But JIT compilers can change the way the code is compiled and they can inline statements, so basically squash them together. So rather than going around the loop, actually stack everything in a sequence. You can imagine with CPython, if it had that feature, like how much faster it would be at that particular problem. PyPy isn't the only Python JIT out there, actually. Number is another JIT compiler specifically targeted actually for NumPy usage. You can use Number by importing a JIT decorator and wrapping just a function with that decorator. If you're doing tight loops or any kind of repetitive number crunching, Number is actually a really great alternative to CPython. Actually, you use it with CPython, so it's more that you wrap the JIT and pick particular parts of your problem set that could be optimized using Number's JIT, especially if you're using a lot of NumPy. So this isn't the only alternative when it comes to removing the overhead of the evaluation loop. When CPython runs functions that are in compiled C extensions, so that's one of the big benefits of CPython, is that it works really nicely with compiled C code. The bytecode is a single operation. So if you want to call a C function, that is a single bytecode. All of the tight loop can happen on the right in this diagram over in a compiled C binary, but this doesn't really answer the original question of why Python is slow. It's actually just saying if we just move it all to a compiled C function, then Python is faster, but you've basically solved the problem by using C and not Python. So if JITs are really fast, then do all of the compilers on the benchmark that we showed earlier, they must all have a JIT, right? Well, again, no. So there's AOT compilers, so Rust, C, C++, but these are all strongly typed languages and they will have static memory allocation or dynamic or automatic. They work very differently into the way that Python or even Node or Java or C# allocate memory and work with objects. So it's really chalk and cheese to compare Rust or C or C++ with Python. A fairer comparison actually is Node.js. So Node.js is the server-side JavaScript runtime,
Those comparisons
but
are
on the Chromium
heartbreaking.
V8 engine. The Chromium V8 engine is the JavaScript engine that sits in the Chrome browser, and it's also used to power a number of other things, including Electron.js apps, which you've probably got on your desktop. I mean, Slack is one good example of that. But you can see that on the benchmark, Node's actually massively faster than Python. So JavaScript has more similarities to Python in terms of its language and dynamic typing, for example. But earlier I mentioned how JIT compilers use an intermediate representation. So CPython also has an intermediate representation, which is a graph of basic frame blocks. So when your Python code is compiled, the execution sequence is determined and the compiler emits frame blocks in a control flow graph, which I talked about before. So if you take a simple for loop, that actually has many parts, so it actually ends up as many frame blocks, not just the one for the entire for loop statement, because inside the loop you could have a block which could call some other code which could then call another frame. Also you can have else statements in for loops, which I never quite understood why, but you can do it. So a control flow graph actually for a for loop could be quite complicated, but it's rigid. It says this is how the code will execute. All of this is sent to the assembler and then it spits out the sequential bytecode. If you contrast that to a JIT, which compiles later on, then some intermediate representations that JITs use are actually a lot more flexible in terms of the execution path. So the code will run the way you expect it to run. That's not the point. It doesn't surprisingly go off on a different branch. It's more about how the compiler actually looks at the blocks of code or the statements or the operations and also the values that make up the code and how it decides to actually send those to the CPU to be executed. This is really about making sure the CPU is being used in the most efficient way possible. So one intermediate representation property is called static single assignment. So if you look at V8's JIT optimizer, so this is the optimizing compiler for V8. It's called Turbofan. It does some really cool things with static single assignment intermediate representation. So all values and operations. So in a Python equivalent, that would be all variables and all operations, all parts of a statement. All of those things become nodes in this massive graph. Python's kind of got a similar thing with AST, but when it actually comes to executing, it's all in sequential bytecode. Whereas if you compare that to Node, basically all that stuff becomes nodes, oddly enough, in a massive graph. And the graph isn't determined in terms of like, here are all the edges on the graph and here's how it should execute. The graph is actually determined in terms of dependencies and data flow. So the compiler's optimizer actually makes decisions about hot code and dead code, and it draws edges in the graph to optimize the way that the code is executed. So by finding dead code and making sure that that doesn't get scheduled, or finding hot code and making sure that that gets scheduled properly, you can make some massive efficiency gains. So that's one of the reasons why in that benchmark Node was so much faster, even though it's dynamic, is because its JIT compiler is able to be really smart about the way that it basically optimizes certain parts of your application. So V8 isn't the only JIT to use SSA. Most modern JITs use SSA as well, including PyPy, and Numbers JIT also uses a SSA representation. So if JITs are so great, why can't CPython have a JIT? I've kind of mentioned the clue a few times. CPython and C extensions go hand in hand. Half of CPython is in Python and the other half is in compiled C code. Compiled C code cannot be JITted. It is rock solid. It's not going anywhere. For a JIT to be effective, the JIT compiler needs to be able to make assertions about the code structure and the data flow and the way that it's being executed. But from Python's perspective, the compiled C modules then become a black box. Like, you don't actually know what's in them, and you can't see the control flow inside those compiled modules. So the JIT could really only work on the Python side, and then you'd kind of have to stick a JIT with AOT compiled C code, and you're not going to get anywhere near the efficiency gains that you would have in just like a pure JIT compiler. So this, I guess, is one of the reasons why CPython can't have a JIT compiler. Something else about JITs that I haven't mentioned is that they have an overhead. So, all this clever optimization like has a cost. Firstly, they have a memory overhead. I don't know if you've noticed, but Node uses quite a lot of RAM. That's not the only reason why, but the JIT is quite a complex piece of software and it doesn't come for free. Second, they have a startup overhead. So for a JIT to basically get running, it has a startup time. So if you stuck a JIT in CPython would take longer to start. Now, that might not sound like a problem for most people who just type Python at the command line and the REPL comes up, quickly. The CPython compiler as well was never designed to be optimized for a particular problem set. It's supposed to be general purpose. And the compiler, and it says in the design notes of the compiler, is supposed to be simple. So introducing a JIT would really go against the design principles. And sure, you could optimize a particular problem set like the tight loop problem that we discussed, but there are actually other ways you can solve that problem anyway that exist at the moment. So it's not to say that CPython doesn't have any optimizations, because it does. It has something called PGO, or profile guided optimizations. The CPython source code is compiled to make a binary, and then that binary is then given. So Python is basically run with a test application. The test application is actually the part of the unit test program, but under test, the application is profiled, and then it's seeing which parts of the Python binary are used the most. This spits out something called a profile, and it identifies what hotspots there are on the app. Those hotspots are then basically like optimized just in the same way that a JIT would, but that's done once. So that's done before the version of Python is built for you all to download. One person does that. So the release manager probably runs the PGO process, and the profile is basically like hard coded into the CPython binary. If you want to run your own profile, you can download the source code and run your own profile. But you're probably going to come up with a similar answer, which is that there are parts of the CPython binary which are run a lot, and those include things like dictionary key lookups, hashing algorithms, stuff like that. There's small functions which are run a lot in the lifetime of CPython, and those are already optimized. So to recap on what almost turned into a talk on JITs, is A JIT can optimize at runtime. An AOT can't make those kind of distinctions. JITs are great for repetitive math-heavy tasks, but for unpredictable tasks, they're not so great, which we'll talk about. If you have those types of problems, then you should use Number or PyPy, and you get a JIT for free, and you get all those big performance boosts. But like I said before, JITs are not free. I say free in terms of cost, but not free in terms of CPU. We were comparing the speed, purely the speed of Node and CPython for the n-body problem.
Okay, so I want to make sure I somewhat understand this. JIT compilers, like the one that Node.js uses, are way faster than Python. But the way that Python is designed doesn't allow for JIT optimization, partially because Python needs to have compiled C code, which doesn't allow JIT compilation because it's static, I guess. And PyPy attempts to recreate the sort of JIT logic that's used by Node.js and Numba, I guess. So I guess essentially repetitive mathematical operations will be better for PyPy and Numba. I mean, repetitive mathematical operations seems like all of programming, so that's not a super helpful description. But okay.
Actually, if you go and look at the benchmark, Node did actually finish that task, great, but it used over 4 times more memory. So if the Achilles heel of CPython is these small tight loops, then what about other types of tasks? Like which types of tasks is it good at? Like which ones is it efficient at? One of those tasks is text processing. So another benchmark is basically doing regular expressions over random DNA strings. CPython is significantly faster than Node.js and is actually in the same league as some statically typed algorithms. So it's not all bad news, and there are applications where CPython's compiler design is actually quite efficient. But this is all about slowness, and it's not just about compilers. So are there any other optimizations that CPython could have? What about memory allocation? So not just on the amount of memory, but also how CPU is used, allocating and deallocating memory. So whenever you create objects and you destroy objects, which actually happens a lot in the life cycle of an app.
It's interesting that Python is actually faster for some things.
Objects come and go as you bring functions in and out of scope, for example. So how efficient is CPython at actually doing that? Because that adds both memory and CPU hit. A good benchmark to look at would be the binary tree benchmark. This particular benchmark basically constructs, traverses, and destroys binary trees again and again and again. It's a good benchmark to use for memory allocation overheads because it indicates a lot about the garbage collection algorithm, and it also looks at if it uses a GC, and it also looks at the cost of memory allocation. So creating all the nodes in those binary trees essentially is allocating memory and deallocating memory. So because Node has a similar memory management story to Python, I'm going to pick on Node again. CPython has 2 strategies for making sure your apps don't eat all your RAM. The first one is simple. Everyone should understand this. It's everything in Python is an object, right? So every object has a reference count. If that count ever goes to 0, the object is destroyed and the memory is freed. But if you have container types like lists, dictionaries, sets, for example, they can reference themselves, which you might think this is a slightly contrived example, but it actually happens a lot more than you'd think. Even just starting Python, this happens. I think I tested it. It was like thousands of times it creates cyclical references. So if you just relied on a reference counter, the memory would balloon and the process would blow up. So another tool is used called garbage collection, which basically looks at cyclical references and then reduces those down so the object can be freed. CPython has a stop everything garbage collector. So after a certain number of cycles, it will ask every container object to check itself for cyclical references. So it will go and find every dictionary, every list that's been allocated in the whole application space, and it will go and ask it to check to see if it has any cyclical references. So that's only done every now and again. It's only done every certain number of cycles because it's quite costly to the CPU. It then goes and marks the ones that are required for removal. So if it has cyclical references and it reduced that number and it gets to 0, that object is actually never referenced by anyone, so it can be freed. This happens on the main thread. So whilst all this is happening, whilst every dictionary is being checked, every list is being checked, nothing else is running. No other operations are running on that CPython process. So if you compare that, for example, to the V8 engine, which follows a similar strategy, it has a stop everything garbage collector, but it actually uses a slightly different technique to make that faster. Because it's stop everything, the time taken to stop, you want it to be as small as possible. So the traversal and the marking of objects, it's actually done on 2 helper threads. So it's done basically in parallel before the main thread is paused. It means a lot of the sweeping process is done in a shorter period of time, and the main thread is only paused for a fraction of the amount of time it would be otherwise. So it might sound like a small difference, and it is milliseconds. But in certain benchmarks, and definitely a lot of applications, if you're hitting the GC a lot because you're allocating and deallocating objects, then this kind of optimization is going to make a pretty good speed improvement. So on that particular benchmark, it's going to become really obvious because this binary tree problem is basically going to hit the GC thousands of times. So it sounds like a fancy feature. So why can't CPython have one of those? So to take a quick pause, the Chromium engine is developed and owned by one of the biggest companies in the world. It's a company that makes billions of dollars in profits. And the Chromium project, like I was looking at on GitHub, and I can see at least 30 people who are working on it full-time, 5 days a week, and they are all very experienced developers. So even if you were just to work out like the cost of running a team, 30, maybe it's probably more, 30, 50 developers running on that, I don't think that's actually a fair comparison. CPython is a community-run project. It's developed by volunteers. All of the people who write and work on the CPython compiler have day jobs. So I actually feel mean comparing Node.js to CPython, because I know the people who work on CPython, and like they're all super smart people, but they're volunteering and they're doing this in their spare time. So to say, look at all these shiny features you can get if you've got $10 million a year to spend on development, that's great, but like as a project we don't have that. So sure, the GC could be multi-threaded, I mean technically it's possible, and I don't think it has anything to do with the guild. That's not the reason why it hasn't been done already. It's just about who's going to do it, who's got the time, and who's got the experience. So that's my pause. I just want to say that because I know that some of the people watching this show, some of the people watching this video, will be on the dev team, and it feels like I'm just attacking the project, which I'm really not. So on the topic of the GIL, is that actually what's killing performance? This is not a GIL talk. So for CPU intensive tasks, if you want to run them in parallel, then there are solutions to do that in CPython today that get around the GIL. So multiprocessing, the multiprocessing package is a great solution. All you need to do is figure out how do you split your workload up into big enough chunks that the overhead of starting a new process doesn't become impactful in the execution time. Alternatively, Number can do a no-GIL JIT, which is pretty nice. Multiprocessing, like I mentioned, does have an overhead, not just in starting a separate process, but actually like the overhead of running the process. But it doesn't really matter as much, because if you're saying parallel, then how many CPUs and how many cores do you have? If you're talking 4 or 8, then running 8 Python processes is not a significant overhead. If this is not that type of problem, then async IO and multi-threading are actually a better solution. So in this benchmark,
Sounds like what it comes down to is that V8 just has way more money behind it, which is what I've heard before. That's the justification I usually give when people ask why JavaScript is faster. So I guess that's all it is. Well, At least that was the main takeaway I got
This is
for
actually
the
one that
memory
I wrote.
allocation part.
This is a TCP port scanner used for testing purposes, which I just wanted to see, like, if you wanted to run a task concurrently, like checking 20 TCP ports, each with a timeout of 1 second, then how close does each approach get to 1 second? Because the minimum is 1 second, because if one of the ports is closed, then it's going to time out after a second. But how close does it get to that? So async IO is the fastest, because this is a IO problem. This isn't a CPU problem, so the GIL's got nothing to do with it. In this particular benchmark, async IO is actually the best approach because it's got the smallest amount of overhead in terms of running concurrent tasks. But sometimes you've got a problem which is both IO bound and CPU bound. So in those cases, the new solution, which is going to be coming in 3.9, is subinterpreters.
Yeah, their
which is going
funding
to be
was
the new
pretty high
hotness,
too.
and
They
I'm
must
super
have
excited
to.
about it. But
They have
it's
to
still
have a
experimental,
few
and
like full-time
basically it gives
people,
you the
don't they?
ability to run multiple interpreters rather than multiple processes, and interpreters have a much smaller footprint. Also, it's a bit easier to share memory and stuff between interpreters, but definitely not as easy as async IO. So if you have a problem that's CPU bound and IO bound, then this potentially is a great alternative. So in summary, modern speed with modern compilers is about optimizations. Tight loops, like the tight loop problem, really hurts CPython. Its compiler is not designed for that problem. And if you look at those benchmarks, it's going to look awful. But not all problems are a tight loop problem. If you do have that problem, other implementations are available. Parallelism improvements are coming in 3.9 and 3.10 in the form of subinterpreters, and there's still quite a lot of work to be done there. If you do want to chip in and help out with that work, that would be awesome. I think the GC potentially could be optimized and improved, but I wouldn't expect to see like a massive improvement for just general problems, the general applications. In some problem spaces, the GC optimizations could actually make a pretty decent difference. But lastly, optimizations cost money and they cost time and they cost effort and they cost planning. These are complex things. This is not a simple thing that we can just go and hack in a few lines of code. And CPython is general purpose. So if we make optimizations, optimizations come with compromises. And
Yeah,
there
that's what
are
it looks
optimizations
like.
available. There are.
I was looking at. I was like, well, what in the world is this graph? They're plotting millions of dollars, but then the units are dollars. Why? Why don't they just put an M here? Okay. Like I was thinking, there's no way they have $4,000, and that yeah. Anyway,
Other approaches to Python. So my leading question, is Python slow? Well, actually, the answer is you can pick different interpreters, and the interpreters have been designed to different problem spaces, and each of those interpreters have been optimized to different problem spaces, and actually are very fast. So if you pick the one which is general purpose and you apply it to a problem space which it wasn't designed for, if you measure a fish by its ability to climb a tree, you're not going to get the best outcomes. So finally, I hope you enjoyed my talk. It's been really fun to give this talk, to do the planning. Also, I am working on, finished now, a book on CPython internals, which I'm publishing with the Real Python crew. This is going to be out as a physical book in a month or so. If PyCon was going to be on face-to-face, we were actually going to have a pile of books at PyCon, so it's a real shame. But basically, I dig into the compiler, actually just pretty much everything that's in CPython in the source code. Anyway, it's a real technical deep dive. Check out my website. If you have any questions, email me, or you can find me on Twitter at the usual address. So thank you very much. And again, thank you to the PyCon team and the PyCon committee for making this happen. And please donate to the PSF. Goodbye.
that was fun. You obtained it. Obtained. How do I... There. The story that someone told me when they first told me that JavaScript is the fastest interpreted language in the world because I was a Python fanboy, at least more than I was a JavaScript fanboy for a long time. Is that when it became apparent that JavaScript was going to be the dominant language for the web, all of these browser companies, all the companies that made browsers wanted to be able to say that they had the fastest or the fastest JavaScript interpreter. Because of course they'd want to be able to say that. And you start begging. And so oh wait, did my internet disconnect? It says disconnected. And so obviously Microsoft wanted to be able to say they had the fastest one, so they dumped a ton of money into their whatever their browser was called. Internet Explorer, I guess. And so then, Google wanted to be able to say they had the fastest. They dumped a ton of money into V8. And Mozilla wanted to be able to say the fastest. They dumped a ton of money into, I think it was SpiderMonkey. I think Microsoft has Chakra, the names of their engines. And so all that happened is that there are all these blazing fast JavaScript interpreters just laying around for free. And that made JavaScript the fastest interpreted language in the world. Not for any good reason, not for any like good design decisions or anything like that. Just because it's used in the web, and all these companies want to be able to say they're the fastest one. The Wikimedia Foundation puts Jimmy Wales' face in a large banner. Wait, who is that? Co-founder of Wikipedia. That's nice. What makes JS good for the web? Why can't they use another language? I don't think there's any reason they can't use another language. I think it was just design. It just happened to be the case that JavaScript ended up being used, and then there were more and more optimizations built around that assumption. I do know that the browser was never designed to use a stack. It uses a well, I guess it does have a stack. JavaScript does have a stack. But JavaScript is actually, I don't remember my history well enough. JavaScript is like some sort of a variant of Lisp. Like it runs functionally, and that's done on purpose. I'm not gonna be able to find this. JavaScript is a Lisp. Yeah, I wasn't making that up. Why should they just put Guido's face on the Python website begging for donation? They could. But I think my understanding is that the reason for this, that JavaScript or a functional language was chosen for running the web, is that the web can never block or isn't supposed to block. You shouldn't be allowed to do things like just stop and run a bunch of code at once because it's single threaded. And maybe multi-threading wasn't possible back then or something like that. And so with functional programming, basically everything, a lot of things are expressed in, it's done in terms of small functions that run one at a time. So it's easy to block and go to something else. Or not block, but interrupt and go to something else. But I think that's the only reason. And with WebAssembly, more things can run on the web. JavaScript isn't Scheme. Of course, isn't Scheme is Scheme. JavaScript is JavaScript. There are excellent reasons why JavaScript is nothing like Scheme. Pretty much everything that makes Scheme Scheme is nowhere to be found in JavaScript. One of the fundamental ideas in Scheme is to be minimal and elegant to the point of pain. In early schemes, there was no real block scoping. You had to create block scopes using let as you do today. But let was implemented as a macro that acted like JavaScript's immediately invoked function expression idiom. Likewise, the scheme standard mandates tail call optimization because the philosophy of the language is that if you have recursion, you don't need loops. And there's no real exception system because if you have continuations, you can make pretty much anything you want for yourself. If Lisp is a programmable programming language, then Scheme is an assemble it at home kit for making yourself a programmable programming language. JavaScript does not have this quality at all. JavaScript also isn't Lisp, as people who write Lisp use the word. Agree or disagree, the Lisp community has coalesced around Common Lisp. Anything that doesn't harken back to Mac Lisp is considered not Lisp by experts. You know, Scheme looks a lot like Lisp 1 to everyone else, but hardcore Lispers will tell you that Scheme isn't Lisp, and that the only thing it has in common with Lisp is cons. Seriously. Well, that doesn't sound like he's arguing what he says he was arguing. Nevertheless, I often say that JavaScript is a Lisp, although not Lisp. I say it the same way that I might say that Scottish Lee is a McPherson, even though obviously the surname Lee is not spelled McPherson. The trick for me is context. Saying that JavaScript is a Lisp when talking about Lisp is not helpful. It does not add any bits of information to understanding Lisp. If someone is learning Lisp, I do not suggest learning JavaScript first. This person is not saying anything interesting or nothing related to the web. This is like a very semantic, I feel, argument. Big deep talk, yeah. Call a Lisp function from JavaScript? Okay. I'd have to do more research into figuring out why JavaScript was chosen for the web. I think it was a pretty interesting story. I just forgot it. Maybe I can just Google this. Well, that didn't work. I hate my internet, man. And it's funny that, wait. Yeah, this still doesn't say I'm dropping frames. Nice. Is Google down? It goes down sometimes, but it's not that often. Yeah, I can't find the story. There's like a story behind why JavaScript was chosen. All I said is it goes down sometimes. It's not that helpful. Also, trying to program while also listening to a video is hard. I've watched some streamers either just stop what they're doing and watch a video, or play some fairly repetitive video game and watch a video. But doing it while programming is not that easy. It doesn't help that it's kind of hard to figure out how to use this. I haven't been able to find a good example on how to use this with PNG images. Anyway. Purchase and listen to podcasts, I see. I always thought it'd be cool to be able to do stuff in the background while programming, but like, damn. I guess Tetris is fairly, at least from what I know. Okay, use a different part of your brain. Like if I was trying to do a Sudoku puzzle and watch a video, I feel like I could never. Like it requires so many memory allocations to do Sudoku, basically. Video games and music for sure. Especially for fairly repetitive video games. I feel like that's the only way I'd really play video games as an adult. Well, not necessarily, but it's a lot more common than just stopping what I'm doing to play video games. Create a video from PNGs. Tetris is completely allocated to the subconscious part of your brain. That's nice. So then you can do a lot of things while doing that. And during my crazy college days, I would quote unquote prove that I wasn't drunk to people because I could always juggle regardless of how much I drank. And there's two tricks behind this. The first is that I never actually drank that much, like pretty much ever. So I was never really drunk. And then secondly, you can get very drunk before you can stop juggling if you know how to juggle. It is like, it's so much muscle memory, but like most people wouldn't know that. Juggling seems very hard. Yeah, that's I heard a very smart person told me once that how difficult something seems before you have any experience with it tells you very little as to how difficult it actually is. And juggling is a prime example of that. But juggling's, you'd be able to learn how to juggle. Rubik's Cubes? Yeah, probably. Yeah, Rubik's Cube probably will. I've been looking for a way, pretty much that entire video. I was trying to find a way to convert canvas data into PNGs and use that to turn into a video. I can't find a good example. The basic 3-ball juggle seems not too hard. Yeah, it's not super hard. You could learn it if you really tried. I have faith in you. Suitable output format. Must be something like this. To make a slideshow, use canvas element.capture stream and record stream with a media recorder. I think these are two totally different approaches. Element.toBlob. I think this returns a file path. So this takes a canvas. Canvas.toBlob. I vaguely remember using this. The first time I tried to do this. It copies a PNG image, then appends a new image element. Okay, so this gets the URL. Maybe that's all I need. Although, do all canvas elements have this toBlob? to data URL. It turns a data URI, being a representation of the image in the format type specified by the type parameter. Data URL. I think this is what I used before. This is what I want to do. Pipe an image directly to the stream. Store the canvas image in memory. That's what this does. Send this image directly with MFS, as explained in the README. MFS can't parse blobs, but only array buffers. Create a file reader from the blob first, or use worker FS. How do you create a file reader from a blob? Read as data URL. Let's web applications asynchronously read the contents of files or raw data buffers stored on the user's computer. Which I don't think is what I want. Starts reading the contents of the specified blob. Once finished, the result attributes contains an array buffer. That sounds right, actually. So you can do blob.array buffer to convert. I guess this is a blob, the data URL? Or a DOM string. Okay, I just gotta probably just try to do this. See what that does. I think it was already doing it. Does this have two blob or something like that? Oh, it does. That's nice. So this is basically a black triangle, or black rectangle. Do to blob. Argument required. Callback type and quality. Um, I guess I'll do this. Wait, what would I even want to do after converting it to a blob? Probably convert that blob to to an array buffer? And then this person said that MFS can parse array buffers. I feel like I have to be a detective to string all these pieces together. I'll just try running this pretty much verbatim. Well, it didn't. Oh, great. It appended the image. Perfect. So it should be the case that if I can defer this until after I render something to the screen, then it should append a different picture. So I think this can basically do the same thing. Actually, I'll leave that there and just copy it. I'll connect that to a button. Okay. Okay, so now I think if I render an image, then hit this. Nope, it's still black. Darn. I wonder if it has to be redone? Like I have to get the reference at the time when... after it's been updated or something like that? This canvas must be getting updated. Darn, well, I guess I'd rather figure that out later on. It's at least reading reading the image and doing something with that. Now, as for what to do with that image, I really need to figure out what this mounts array even is. Create a file reader from the blob first or use worker fs. This person mounts to /test, but this person is writing to /tmp. Crosses that push. I promise. Which is basically creating an image here. It's saying blobs.map. And this is incorrect. Blobs, and this is an array with a single entry, example.mp4 and data ** blob. I need some better documentation on this. Can mount an other fs. Well, systems ffmpeg.js uses mfs to store the input and output files in ffmpeg's working directory. You need to pass an array of object to mfs out of the following keys: the file name and the data. The resulting object has the memfs option with the same structure and contains files which weren't passed to the input. Array of objects, which is the file name and the data. I think that makes sense. So what I think I'd want to do canvas to blob takes this. This will be like the file config, something like that. It'll be just an array, and I want to append objects to this array. So I want to push. Oh man. And this just needs a name and the data. And just do test.png. I don't know if this is a PNG though. The type. which is downstring indicating the image format. Default is image PNG. Okay. To blob. I'll go ahead and put that in specifically. There, image PNG. And here, the data will be like blob.toArray buffer. Oh, it returns a promise. It would return a promise. So to do that async thing that this was doing. Okay. Okay, so now we should be able to just await this. And if this resolves with the contents of the blob as binary data contained in an array buffer, then that should work now. I'll put this here. Actually, I won't put it there. I'll put it, leave that there. So now this ffmpeg should have that one thing in its file system. That's what you call ffmpeg on an image. Pretty much nothing. Because there's no output. That's fine. I'll try to see if I can make it do that. Print. Okay. So I can call ffmpeg, I won't call it with the version. I won't redefine those. Oh yeah, I will redefine those actually. And all I'll pass in is like test.png. And see if that works. Well, I did something wrong. Reserved word? Does that mean it's somewhere within this function? Append canvas. I don't even need this function, really. Oh my god. At click? Okay, now I'm starting to think there's something up with the server. Nope, still happens. Oh, it's within the await. Okay. Wait, that's how you used await. Await. I see there's a correct way to do this. The response API. Oh, what? A new response? Taking the blob dot array buffer. What is a response? I guess promise wasn't good enough. Use file reader to read the blob as an array buffer. Man, this is such a pain. Well, I'll do the slower version. Just to see if I can get it to work. Oh my god, it still does it. This is within an async function. See, that's a common thing. Oh wait, yeah, this. The function directly enclosing it needs to be async according to your comment. Adding async to the inner function fixes your issue. And this has to be async? Then do I have to do await on this? I must have to. Canvas.to blah, but this doesn't return a promise. I'll just see if this works. Well, it didn't crash immediately, so that's good. Unable to find a suitable output format for test.png. I think that's good. Well, it's not what I see here. When I call it here. Null at whatever. Unable to find a suitable output format. This is from 2019. I guess that's good. I wonder if you can do picture conversions with this. Like to JPEG or something. No, it doesn't work. Maybe if I do -I, I don't think this will matter. At least one output file must be specified. Okay, then maybe here I can do -I. No such file or directory. Yeah, that's bad. Guess I can try it again, but it seems like it's not doing what I expect. Oh, I didn't add the mount. That would make sense. If I'm like MFS or MemFS, that's what I need. And this will be the file config. Damn, it still does it. That sucks. I'll try printing this beforehand. STD out is not defined. Yeah. Oh, it's empty. Oh wait, no it's not. There's the name and the data right there. And then it just calls test.webm here. I fail to understand. That should be an array buffer. Yeah. Has the file name test.png. Darn. probably have to like debug some more stuff with this opts. Blobs. Type mount point opts. It says it can parse array buffers. Let me see if I can find that example. This one doesn't have a oh, it does have an MFS. But there's nothing here. Oh, maybe this is supposed to be used like locally. That could be what's happening. Darn. Array of object. Yeah, I guess something else is wrong. The same structure. It contains files which weren't passed to the input. Yeah, I don't know what's wrong with this. I have to debug that later. Because everything looks right. Oh well. It's been just over 2 hours, so I'm going to call it here. Yeah, so thanks everyone for watching. And I'll see you in the next stream.